Yeah, good morning. In previous lecture, I have discussed the concept of generalized momenta and cyclic coordinate through Lagrangian expression. In this example, I will also explain that how the given Lagrangian profile. If we have a profile of Lagrangian, or if we have a Lagrangian profile, then corresponding to that profile, how to find out the generalized momenta and how to check whether the given system having cyclic coordinate or not. So we have this example, that is example number 1. The Lagrangian of a system is given as 1 by 2 m ax dot square twice bx dot y dot plus cy dot square minus vxy. Means our potential is simply xy coordinate. So for this expression where x dot is simply dx by dt, y dot is dy by dt. So what is generalized momenta and what is the expression of generalized momenta and cyclic coordinates? So let us analyze. We know that generalized momenta is simply del L upon del QK dot is PK, and in this case our PK is simply x and y, because our Lagrangian is in xy or x dot y dot. So we have our k is simply xy. So corresponding we have two different. So del L upon, so basically this QK is simply x and y. So we have two different component of generalized momenta, one corresponding to x and another corresponding to y. So with this example, we can develop our understanding to evaluate the generalized momenta and to check the cyclic coordinate, to check the whether our system is having constant of motion in some coordinate system or not. So cyclic coordinate means if our cyclic coordinate exists, it means in that direction our momentum is conserved. Our momentum is conserved. It means we have a constant of motion. I have already derived that pk is constant from Lagrangian equation of motion. So we will analyze with this example. We will learn that how to obtain the expression of generalized momenta. The purpose of this example to understand the concept of generalized momenta and cyclic coordinate via example. So in this example we have this Lagrangian profile. So our del L upon del QK for x, if we are evaluating for x coordinate x, so our del L upon del x dot, which is del by del x dot, and what is our L? L is simply 1 by 2 m ax dot square plus twice of b x dot y dot plus cy dot square minus v of x y. Now what differentiating this partially with respect to x dot. So if you are partially differentiating with respect to x dot, it means rest entity or rest of the things treated as a constant. So x dot y dot is constant, vxy is also treated as a constant, and differentiation of constant is automatically 0. So what we have, if you will differentiate with respect to x dot, so we have something, we have x dot, and this will 0, this will 0. So what is our, so this will give us simply, let me take 1 by 2m outside. So del by del x dot of ax dot square plus del by del x dot of 2b x dot y dot, and rest will be 0. So what we have? We have 1 by 2m, which is 2a x dot plus 2b x dot will give us 1. So we have 2b y dot. So what we have, this 2 and this 2 will cancel out. What we have simply m ax dot plus b y dot. This is del L upon del x. So del L upon del qk dot is pk. So what is our del L upon del x dot is simply px, and what is the value of del L upon del x dot? From here, this is m ax dot plus by dot. So this is corresponding to px. If we are evaluating y coordinate for y, so what we have? We have del L upon del y dot, which is py. So what is our del L upon del y is del y dot is, it means differentiating this Lagrangian partially with respect to y dot. So x dot is 0, y dot is 1. So we have this expression, and this y dot square is simply 2y dot, and this will again 0. So this is del L upon del y, del upon del y dot. We have this 1 by 2m, which is ax dot square plus 2b x dot y dot plus c y dot square minus v of xy. Now differentiating partially with respect to y dot. So this will 0, this will give only y dot and y dot 1. If we are differentiating this expression partially with respect to y dot, this will give 1. So what we have 0 plus 2b x dot plus 2c y dot minus 0. And we have 1 by 2m outside. So what we have simply del L upon del y dot is simply this 1 by 2m 2b y dot plus 2b x dot 2c y dot. So 2 again will cancel out, and what we have m twice of b x dot plus c y dot. So what is this? This is simply del L upon del y dot, which is py, which is equal to m bx dot plus cy dot. So this is the way to find out the generalized momenta, because our Lagrangian is in xy profile. So we have two component of generalized momenta, one correspond to px and another correspond to py. So del L upon del y dot is simply py, which is m bx dot plus cy. So this is very important question. I don't know whether it is, I don't know in which year. So next check whether this Lagrangian have a cyclic coordinate or not. So to check the cyclic coordinate, what we have to do? We have simply check del L upon, we have simply check, let me just check for cyclic coordinate check del L upon del qk is 0. If it is 0, then we have cyclic, otherwise not. So our again qk is, so we have what we have to check? We have to check del L upon del x and del L upon del y is equal to 0. In this Lagrangian expression, simply we have to check what is our del L upon del x. So let me write what is our del L upon del x. So this is now differentiating partially with respect to x. So there is no expression of x in kinetic energy term. So what we, if you differentiate this potential with respect to x, what we will have? We will have del v by del x with minus sign. Del v by del x. So which is not equal to 0. So there is no cyclic in x coordinate. So again b del L upon del y. Again differentiating this L partially with respect to y. So there is no y term in kinetic energy term. So del L, this term is 0. Again we have del L upon del y is simply minus del v by del y. Minus del v by del y, which is not equal to 0. So no cyclic in x and y. So there is no cyclic coordinate in x and y. So we can say that there is no constant of motion, means px and py not conserved. There is no constant of motion in this Lagrangian system or in this dynamical system or in this system. So this is the way to find out the generalized momenta and check whether the given system having cyclic coordinate or not. If because in this system del L upon del QK is not equal to 0, so there is no cyclic. Our system is no cyclic, having no cyclic coordinate in x and y. So no cyclic in x and y. So it's all about this question, and this is very important question because we can learn a lot about the concept of generalized momenta and cyclic coordinates. So in next lecture we will discuss the another example of Lagrangian.